So in this unit, we're going to be learning about momentum and energy, but today we're going to start with momentum. And you've probably heard momentum used. It's been used in a lot of different things, saying, well, I just got to get a certain amount of momentum. Or as a fat kid, I couldn't stop myself as I was falling down the hill because I had way too much momentum. So momentum, we need to figure out what that is. But to do that, first we need to take a look back. Because we need to remember some things because all of this is connected. First of all, we've just got done talking about force. And if you remember, force is mass times acceleration, right? And before that, we had learned some about acceleration, which was a final velocity minus initial velocity divided by a time. Do a slightly better T. Okay. And so there's all of these different things. And so if you want what momentum is in its basic root, we can just say that momentum is equal to a mass times a velocity. So we use a P to represent momentum. Why? More than likely because we had too many M's. We're already using it for mass and things. So M times V, right? So you might think, okay, well, this looks very similar to force up here, and you're right. It is a mass. It is moving. That's what acceleration and velocity both involve moving, right? The great difference is with a force, if you remember with a net force, you can have something that technically has a net force of 0, but is still moving, right? With momentum, you're always going to have a velocity in one way or another, and it would be a constant velocity to get the momentum. And so your constant velocity means even if it's not accelerating, it can still have a lot of this momentum that's going on. And that's why I use the example of a fat kid falling down the hill, which I very much was the fat kid falling down the hill. But I wasn't necessarily speeding up. I just had so much mass that once I got to a certain velocity going down the hill, I was hard to stop. And that's really what we're talking about here. And in fact, we need to learn one other thing with momentum, because momentum is directly related to things, because your momentum can change, but we're going to need a force in order to change that. And we can see this mathematically if we do a little bit of study here. So if I'm looking at a change in momentum, then that's nothing more than a final momentum minus an initial momentum. That's how we've done change all around, right? Well, we can even simplify this more and use what momentum is and say, okay, well, this is mass times a velocity final minus mass times a velocity initial, right? Those all would be true equivalent statements. In fact, I could probably even go one more, and I could pull that mass, because the mass isn't going to change, and say this is velocity final minus velocity initial. Well, now that's looking very familiar. See this up here with acceleration? All it is we're not dividing it by time. In fact, if I break force down just a little bit, I could even say that I could rewrite force is equal to mass times a velocity final minus velocity initial over time, right? And so now we're at almost the exact same thing. The only thing is the force is different by time, right? And that's where we actually get the term impulse from. Because if you think about this, if you apply a force over a certain amount of time, so if I say that this is force times time, what I'm essentially doing is multiplying that by t and canceling that out. And what I'm doing is I'm changing the velocity. Now we refer to that, J, as impulse. And so this is a force times time is equal to impulse. An impulse is nothing more than a change of momentum. So now we can rewrite that. This is equal to a change of momentum, because you're going to get this exact same thing up here. You're getting that mass times a final velocity minus an initial velocity. It's just that time canceled out up here. So impulse is the change of momentum, okay? And momentum is directly related to velocity and mass, and it all has to do with force, because that means that our force being applied for a certain amount of time is going to change the amount of momentum that an object has. All right, so I cleaned up our formulas here, but I want you to keep something in mind. Because velocity is a vector, then this momentum must be a vector. And because force is a vector, impulse must be a vector, right? And all that means is they have a direction to them. And this is important, because if we're taking a look at an example here, let's use a classic example. So we got a softball, right? And so you have a softball here, and let's make it easy. Let's just say it's 1 kilogram softball, okay? Let's also say that it's already moving its initial velocity, because you would get softballs thrown at like 40 miles per hour, right? Well, instead of miles per hour, let's keep with our SI units and just say that this one's going at 20 meters per second after it left the pitcher. Now, the pitcher applied a force and sent it at that. But remember, this is all straight to the side, so we're not worried about gravity. It's spherical, so there's very little air resistant. So let's go ahead and say that this is a constant velocity that it's now moving at, even though we know that it would be moving downward some. But let's say they threw it up just enough that they canceled out gravity, so it's going perfectly straight to the side. And it's one kilogram moving at 20 meters per second. Well, we can figure out the momentum for this. It's very simple, right? We just use that momentum is equal to mass times velocity, and then we can plug in that it's 1 kilogram times 20 meters per second. And then we're going to get that our initial momentum, because this is our initial velocity, is equal to 20 kilogram meters seconds. Okay, and yes, it doesn't have a derived unit, so that's our initial momentum. Now, at some point in time, it's probably going to hit a bat. Yep, that's my terrible baseball bat. But what we say is this bat is going to apply a impulse force on it, right? So it's going to apply some sort of J. Now, we don't know what that impulse force is, but let's say we can then take another screenshot in time and look at the ball, the softball, that, remember, is 1 kilogram, as it's leaving off the bat. So the bat's no longer touching it. And let's say it's now going at 30 meters per second. But notice our direction changed. So let's make this a negative 30 meters per second. Okay, well, we can come up with a new momentum. And so for that, we're just going to do, this time it's 1 times 30. And we're going to get that our final momentum is going to be negative 30 kilogram meters per second, right? Now that's easy enough. Negative 30 kilogram meters per second. But if we wanted to figure out what that impulse was, then we're going to have to come and we're going to have to use that impulse is equal to that change in momentum, which is equal to momentum final minus momentum initial. And we can do that by simply seeing that we ended with a negative 30 meters per second, kilogram meters per second, minus 20 kilogram meters per second. And what we're going to get is that impulse is equal to a negative 50. Now, I could go ahead and say kilogram meters per second is what you would be thinking, right? But not so fast. This is a negative 50 Newton seconds. Seconds. That's our unit that we're going to use for impulse, is Newton seconds, because we know that impulse is actually equal to a force times a time. And the reason we would look at it this way is because if we looked at that last thing, if this is mass, we can pull the mass out, and this is a change in velocity, then all that is that force times a time. And so these units would derive to be these units of newtons. And I can show you that. If we look at the unit for a newton, what is a newton equal to? Well, a newton is equal to a kilogram times meters times second squared. And if I do newtons times seconds, I'm just getting kilograms times meters times second squared divided by second squared times seconds, which is just going to cancel out one of those, which is going to equal kilogram meters per second, which is the unit we had before. That's why it works both ways. Okay, so those are the same derived units. So we can say that N times S is a derived unit of kilogram meters per second. Okay? Now, with that, we had that it was what? A negative 50 Newton seconds. Well, the interesting thing is if we wanted to understand the amount of force that the batter applied, we would just have to look at how long the bat was actually in contact with the ball. So if we looked back and we were able to measure, and it would probably be, a fraction of a second. But if we could then divide this by time, right? So we now have impulse divided by time, and it's going to give us just the force that was applied. And so if we said that this was at, say, 0.3 seconds, because usually the bat is not in contact with it very long, then we would know that the force that the bat applied is equal to a negative 166 I'm just going to say 67 newtons. And so that's a good bit of force for this. Well, I mean, it's over 100. So anyway, you can see how you can derive and get all of these things just by knowing some time and the momentum.